This report studies the effect of soil creep down a slope. Soil creep is a form of mass movement which is the downslope movement of the Earth's materials under the influence of the Earth's gravity. The detachment and the movement of the Earth's materials occur if the stress imposed is greater than the strength of material to hold its place. Soil creep, also known as downhill creep, is the slowest type of mass movement that cannot be seen with the naked eye and may appear to an observer to be continuous, but is really the sum of numerous discrete movements of individual particles rising and falling. Soil creep has major effects on landscapes and can cause the infrastructure built in these areas to be disrupted. As the soil creeps down a slope over time, it can cause bent tree trunks, terracetes, fence posts, telephone poles and tombstones to be angled down slope, torn road surfaces, and cracks in the walls and buildings of infrastructure. The process of soil creep in the Illawarra is significant as there is a lot of infrastructure built on the Illawarra escarpment, which is characterized by dynamic climate conditions, topography that is mainly steep and highly irregular, colluvial deposits, and specific soil types which all provide ideal conditions for the processes of soil creep. As an example of this, I show that in the Illawarra suburb of Wombara, there are several sites that indicate soil creep, shown by the cracking of retaining walls and disruption of local roads. As this is a process that occurs over a long period of time, in the future there is going to be more and more cases of creep within these soil creep prone areas. Therefore, more research is needed in managing and preventing soil creep to minimise the effect it has on the landscape and infrastructure in these areas. Theoretical background. Soil creep, also known as downhill creep, is the slowest type of mass movement. It refers to the downward movement of rock and soil down a low-grade slope that cannot be seen with the naked eye and may appear to an observer to be continuous, but is really the sum of numerous discrete movements of individual particles rising and falling caused by the expansion and contraction due to wetting and drying or freezing and thawing. When sediment particles expand, individual particles are lifted up at right angles to the slope. When sediments shrink, the particles fall straight back down. Creep takes a long time because each particle might only move a millimeter or a few centimeters at a time. What causes it? Freeze-thaw is a process when the water in the soil freezes and the ice crystals push the soil particles outwards, perpendicular to the slope. However, once the ice melts, this causes the soil to flow down the slope under the influence of gravity. After many freeze-thaw cycles, the soil continuously moves slowly down the slope through expansion and contraction. Wetting and drying. Creep can also be caused by constant alternation of wetting and drying periods, which works in the same way as the freeze-thaw process. As when the soil is saturated, it increases in volume, expanding outwards, and when it dries, it decreases in volume and flows down the slope due to gravity. Heavy rainfall. During heavy rainfall, the now saturated soil increases in volume and weight, which causes the soil to move down the slope under the influence of gravity. Bioturbation. This is the disturbance of sedimentary deposits by living organisms. Roots of plants on slopes force grains of soil apart as they grow. The openings created by these roots then collapse when the roots decay. Small animals also burrow, creating tunnels through the soils, which also allow water to be collected, and then they eventually collapse, causing soil creep. Thermal contraction and expansion. Thermal expansion occurs when there is a change in temperature that increases the average molecular kinetic energy as the molecules are moving more readily and therefore have a greater separation average. Thermal contraction occurs when materials contract on heating within certain temperature ranges. This expansion and contraction causes soil creep in the same way as a freeze-thaw process. Process that affects soil creep. There are a range of factors that affect the process of soil creep. The rate at which soil creep occurs down a slope depends on the gradient of the slope, water absorption, type of sediment, vegetation, and the weather in the area. These factors work hand in hand in deciding whether or not the soil will progress downward and how fast/extensive the soil creep will be. Gradient of the slope. The steepness or gradient of the slope and the rate of soil creep have a direct relationship. Creep occurs when the friction produced from materials resisting gravity move against each other. As the gradient of the slope increases, the gravitational force that is perpendicular to the slope decreases, resulting in less friction between the materials, causing the soil to slide downwards. Water absorption. When determining water absorption, there are three main factors to consider, which are permeability, porosity, and water retention. These all influence the accumulation and distribution of the water in soils. Permeability is a measure of the ability of a porous material to allow fluids to pass through it, whereas porosity is a measure of the empty spaces within the material, therefore indicating how much water it can hold. Whereas water retention is the material's ability to hold onto this water. Water absorption is therefore clearly a factor that affects soil creep, as an increase in water correlates with an increase in volume and weight, which speeds up the rate of soil creep. Type of sediment. The type of soil is a major indicator of whether or not creep will occur. Different soils have different characteristics and are usually distinguished by their texture. The four most common types of soil are sand, loam, silt, and clay. Sandy soils are the finest type, with loose particles, whereas clay soil is the most compact and heavy and has good water retention. Therefore, this affects soil creep, as how tightly packed the particles are and a soil's ability to retain water are two characteristics which govern the rate of soil creep down a slope. Vegetation. Vegetation has a massive effect on soil creep, as root systems from trees and shrubs can build an interlocking network that holds soils in place. This acts to stop the overall downward movement of soil materials. Weather. Weather is the state of the atmosphere to the degree that is hot or cold, or wet or dry. It generally refers to the day-to-day temperature and precipitation activity. The weather of an area controls the temperature and amount of water it receives, and is therefore a major factor that affects soil creep, as temperature and water are the main drivers of the process of wetting and drying or freezing and thawing. The weather in an area can also have an effect on the rate of which soil creep occurs, as the amount of water present in the soil is a major feature that determines the rate of creep. Although water does offer cohesion, which binds soil particles together, if the soil becomes too saturated due to extensive precipitation, water fills the pores between the grains, creating a slip plane between the particles. This offers no cohesion, causing the ground to slide along the slip plane it creates. Evidence of soil creep. The downward movement of soil down a low-grade slope is a very slow process that causes significant damage because it is a widespread phenomenon that is likely to be occurring to some extent on all soil-covered slopes. It cannot be seen with the naked eye, and therefore we rely on observations of the effects of creep to see where it's occurring. These include curved tree trunks, terraces, fence posts, telephone poles, and tombstones angled down slope, torn road surfaces, and cracks in walls and buildings of infrastructure. Curved tree trunks. Trees tend to emerge with straight vertical trunks because their growth hormones are strongly influenced by gravity and they will generally grow towards the direction of light. However, plants located on hillslopes tend to have bent tree trunks. This is because as the soil is slowly moving downwards, the tree on the slope is also growing upwards slowly, which results in the curvature of tree trunks over time. Terraces. In geomorphology, a terracete is an irregular step-like formation on steep hill slopes. It is formed when saturated soil particles expand, then contract as they dry, causing them to move slowly downhill. Fence posts, telephone poles, and tombstones angled down slope. As soil slowly creeps down a slope, structures such as fence posts, telephone poles, and tombstones that are normally upright also move downward with the soil, causing them to be angled down slope. Torn road surfaces. Soil creep will cause roads to be disrupted due to slow underground soil movement down the slope. It causes the hard road surface to be disrupted as they are not flexible, and as the soil moves downwards, this road surface will crack under pressure and also begin to move downwards slowly. Cracks in infrastructure. Soil creep has detrimental effects on the infrastructure built on top. Walls and buildings are rigid structures not built to move, so when the soil beneath them begins to move downward, the effects are seen as extensive cracking and displacement. Application to the Illawarra. The process of soil creep in the Illawarra is significant as there is a lot of infrastructure built on the Illawarra escarpment. The Illawarra area is characterised by dynamic climate conditions, topography that is mainly steep, and specific soil types which all provide ideal conditions for the process of soil creep. The signs of downhill creep are subtle, and therefore building designs within this area must account for it. In general, the Illawarra has a characteristically moist climate with no major dry season. Rainfall is fairly evenly distributed with approximately 1,500 mm per year falling on most of the escarpment. Along with this rainfall, there are also high temperatures, with the hottest month, February, showing an average of 26 degrees Celsius. Hence, this alternating climate of high rainfall and high temperatures increases the chance of soil creep occurring, as it relies on the process of individual particles rising and falling caused by expansion and contraction due to wetting and drying or freezing and thawing. The topography of the Illawarra escarpment, which is mainly steep and highly irregular, promotes ideal conditions for a creep to occur, as the steepness or gradient of the slope and the rate of the soil creep have a direct relationship. Therefore, this topic is very significant when designing infrastructure located in these areas. The soils of the Illawarra escarpment are influenced by the downslope movement of both debris and water. They display contrast between sandy and clay horizons, which are both prone to soil creep, as sandy soils are loosely packed and can move downslope easily, and clayey soils because they are able to retain water efficiently. Because of this, when building in this area, soil creep has to be taken into account. As an example of this, I show that in the Illawarra suburb of Woomera, there are several sites that indicate soil creep. This is shown by the cracking of retaining walls and the curvature of trees. The main case study this report will focus on is a 3-lot subdivision at 95 Morrison Avenue, Woomera. As this site is located on the escarpment, which is prone to soil creep conditions, it is very important to take the right safety precautions and geotechnical investigations in order to minimize soil creep effect on future infrastructure, as some effects are already present. The site located at Morrison's Avenue is characterized by well-maintained short grass with some scattered boulders present. The site topography is hummocky and irregular. The soils in this area range from silty clay to gravelly silty clay, which are very prone to soil creep as it is loosely packed clay, and therefore it means it can move downslope relatively easy and also retain water efficiently. Evidence of soil creep at the site. The eastern wooden piers on the associated decking have cracking in the cement rendering, and a masonry wall is leaning downslope. Some mature trees on the steeply sloping land on the lot are immediately leaning eastward downslope. Conclusions and perspectives. Overall, the mass movement type soil creep is one that we know least about, as it's an imperceptible process that is difficult to discern directly, as it cannot be seen by the naked eye. Some of the problem relates to the difficulty of detection, as observation of effects of creep after they have already happened is usually the only indicator of the problem. This is not economically efficient, as once it's noticed, the damage is already done and is very difficult to counter. Although movements associated with creep is slow, it causes significant economic damage because it is a widespread phenomenon that is probably occurring to some extent on virtually all soil-covered slopes. As this is a process that occurs over a long period of time, in the future there is going to be more and more cases of soil creep within not only the Illawarra but all over the world. Therefore, this is a very important topic to the building industry, as there is only a limited number of flat surfaces that can be built on, and with the rapidly expanding population, the process of soil creep needs to be overcome so that more sloped areas can become more inhabitable. Where construction is necessary, buildings should be anchored to the bedrock beneath the creeping soil and debris layer, but this can still cause gathering of the soil against the walls at the bottom of hills and cause constant strain on the infrastructure. Right now, the best response to the problem is avoid building in areas undergoing soil creep, but in the future, more research is needed in managing and minimizing the effect it has on the landscape and infrastructure in these areas.